This lecture aims at providing an illustration of how electrical and mechanical components can be used to define a more complex and more useful system. For that purpose, I will consider a mechanical system consisting of the following. On a flat surface, a cart is moving. The cart is moving with the help of a motor, and the motor is located here, and it's an electric motor. We assume that there exists a power source that can feed into the electric motor, and for all practical purposes, you may imagine that this is a train where the power may be taken from above the train through a power line or along the rails from a powered rail. In the case of MARTA, it is a powered rail. MARTA is the Metropolitan Atlanta Rapid Transit Authority. The same systems are in place in cities such as Washington, New York, Paris, London, and many others. The variables that we're going to consider are the speed v of the train. Indeed, what we want to do is do speed regulation and therefore what is also named cruise control. So for that purpose, I will give you a circuit together with the mechanical system that does the right job. The circuit in principle looks like this. Okay. We have a desired speed. And we have an actual speed, which we compare by taking the difference between the two of them. If the desired speed, or if the actual speed is lower than the desired speed, what we want is to amplify that signal by a factor k and feed that into the cart, so literally the motor that drives the cart, in such a way that the output speed can be measured and fed back into the system. You can clearly see what happens. As long as V is different from V desired, there will be an input into the system which will be a voltage, such as that voltage tells the electric motor and therefore the cart to move faster up until V reaches V desired. If V is greater than V desired, then that signal becomes negative. The resulting voltage changes sign, and the cart can now slow down. Now, what I want is to do two things. First, put everything into equation. Second, build the logic. And third, do simulations. Okay, so we're gonna do all this and see what happens. So, to begin, we will talk about the equations of motion of the mechanical system. So let's try again to delete this picture, and let's remember the mechanical system. For that purpose, I will consider that the mechanical system is the cart, the motor, and a sensor to measure speed. The equations of the cart are m v dot is equal to the force applied by the motor time plus maybe other component like friction. Now, for the purpose of our analysis, we will remove not the force of the motor, my mistake, but the friction. So we keep the force and we remove the friction. In other terms, once we launch the cart keeps going. Now, let me draw this cart here as a reminder that we are dealing with the real world. Let's now, so this is the cart. Let's now talk about the mother. The equations of a mother, which we will not keep for too long, are omega dot is equal to one over Im, the inertia of the mother, times Kb times I, which is the counter or the back EMF, back electromotive force, electromechanical force on the motor, minus B1 omega, which is the friction, minus, minus Q, which is the force, or to be more precise, the moment that is being applied to the motor. Internally, we also have that I dot is equal to, so where I dot, let me rewrite it as ddt of I, is equal to 1 over L times minus R times identity minus Kb omega plus the input voltage. So let me clarify what I meant here. I meant Kb times omega. Okay? So that is for the motor. Now, for the sensor, we are going to use a smaller motor with low inertia and low everything. We will assume that this motor directly measures voltages, and it is used therefore as generator. Under these conditions, and last, we will use it open loop. That is, the motor shaft will be used to be rotated by the cart, and out of it will come two connections across which we will measure a certain voltage. Okay, and we will call it voltage sensor to differentiate it from other voltages we're going to see. It turns out that the voltage that you measure here, voltage sub S, is proportional to omega. So we will call it K times omega. So this is, again, for the sensor. And I consider this to be the entire mechanical system. Let us see the transfer function of that entire mechanical system. What we would like is some relationship that links the voltage applied to the motor to the speed of the cart. For that purpose, I will make another assumption, and it is the relationship of the speed of the measurement motor to the speed of the cart. Using the appropriate gear mechanism, we can say that if we call omega s the angular speed of the measurement motor, okay, which is used as a generator, pretty much like in a Prius when you are in braking mode, or like a dynamo as mounted on your bicycle. We write that there is a relationship between V and Vs, and we will write it, and omega s, and we will write it as V, the speed of the motor, of the cart, is equal to small r times omega s, where small r is the radius. It is a gear ratio, or it is a radius, for example, of the diameter of the wheels as they are connected to the little motor. It may be more complex depending on the kind of gear ratio you have between V and omega s, but eventually it will have the unit of a distance. To derive these transfer functions, we will erase the board and start getting into the Laplace transforms. I will assume that the initial conditions for all these systems are 0. As a consequence, I can skip the initial conditions in the writing of the Laplace transform. Let us begin with the easy one. M V dot is equal to F. In the Laplace domain, that becomes V hat. I will eventually skip that because I don't want to draw too many hats. Is equal to F hat divided by S times M. Okay. Next, we look at the motor. Okay, this is for the car. Now for the motor, we have these two differential equations, one in omega dot and one in I. The first equation in the Laplace domain becomes S times omega is equal to 1 over Im times Kb times I. Again, I skip the hats for notational convenience. Feel free to add them if you want to do so. Minus Q, which is the torque applied to the system, applied to the motor, or that the motor applies to the system, which is the cart. What we can say is that Q, the torque applied by the engine to the cart, must be proportional to F, and we will say that it is equal to F, the force applied to the cart, divided by, multiplied by a characteristic distance, which can be some sort of moment arm. Okay, so we call L that distance, which is some kind of moment arm. Between F and the resulting Q. The other equation taken in the Laplace domain is S times I, the intensity, is equal to 1 over L, the inductance of the motor, times minus Ri, the resistance of the motor, minus Kb omega, which is the angular velocity impact on the back EMF, which results in an opposite torque, plus V, the voltage, so that's the back EMF, sorry, plus V, which is the voltage applied to the motor. To simplify things, let us put the intensity-related variables to the left. And we obtain that I times S my mistake, times S plus R over L is equal to minus KB omega plus V. Or, in other terms, we can write that I is equal to minus KB omega divided by S plus R over L plus V divided by S plus R over L. Now we can plug this expression into the expression for omega, and we obtain that S times omega must be equal to 1 over Im times KB times I, so it becomes KB times minus KB omega divided by S plus R over L plus KB times V divided by S plus R over L. Oh, since I have a potential like notation clash between this V and that V, let me correct that right away. I will call voltages V but in capital letters instead of what we have now. 1, 2, and 3. And 4 to go. And of course, we still need to add the minus Q, which is the torque applied to the motor by the cart or by the motor to the cart. When we put things together and we put all the omega terms on the same side, we obtain that omega times S plus 1 over Im. So we're going to put KB squared here on top, divided by Im times 1 over S plus R over L close parenthesis must be equal to KBV over IM S plus R over L minus Q divided by IM, and that's it. So here is where our engine stands, and we can finish our transfer function computation. By erasing, oopsie, that's not what I wanted to do. Erasing the equations to the left and simplifying the expression to the right so that we can get an appreciation for how ugly it is. I don't know how this happened, but let me do it again. We erase this guy, and we erase this guy, and we finally erase this guy. Okay. So we eventually have that omega is equal to 1 over S plus KB squared over IM times 1 over S plus R over L times so let me make a parenthesis here. I said times the following expression, KB V divided by IM times S plus R over L minus Q divided by IM. This represents a fairly complex equation, and it might be useful to understand how to simplify it. The way to simplify this equation is to go back to the equation on intensities and to say that intensities establish themselves to steady state faster than the motor can reach its mechanical steady state, that is, rotates at constant speed. If you remember, the equation on I was d dt of I is equal to 1 over L times minus Ri minus Kb omega plus V. A way to assume that I gets quickly to its steady state value if I keep V constant is to erase the di dt. And therefore, in the Laplace domain, erase the s that comes with s times I. The s that comes with s times I appears here on the one hand, and there on the other hand. We therefore erase them. The transfer function from voltage to omega and from q to omega then simplify greatly. And if I erase some of this material, I can obtain the following expression. Let me just finish erasing all this. The expression becomes omega it must be equal to 1 over S plus KB squared over IM times L over R. Multiplied by KB V divided by IM L times R minus Q over IM. Now, the equation of omega can be linked to that of the current. And by doing so, we obtain the following. Erasing first the intermediate computations for omega, we write that V is equal to F over Sm we then have omega, or we have F is equal to, so R times F is equal to Q, that's the transmission of force, and then we have this expression. So what we're going to do is we're going to say that V, the speed of the car, is equal to Q over R times M times 1 over S. Then we get Q from this equation. Q is equal to Im times omega times S plus KB squared times L over RIM plus Im times this expression, or to be more precise, we must add a minus sign here and a plus sign here. So Im times this times that, where V is the voltage, simplifies to R times KBV divided by L times V, the voltage across the armature of the motor. When I plug this in here, I obtain that the motor's expression, the expression for the motor speed as a function of the input V will be V equals minus Im divided by, or times rather, omega, times S plus KB squared L divided by RIM plus, and of course the whole thing divided by S times R times M plus, okay, so let me just make this fraction more explicit, RB or R times KB again, let's make a little separation here, times V over S times R times M. All right, so this is where we stand. In this expression, we still have omega appearing. In order to simplify that we will first remove this expression, and second, remember that omega is a function of the speed of the cart. I can erase this as well. And right. That the relationship between omega and V satisfies omega times some characteristic radius r must be equal to V. It's like a gear connection between the motor speed and the speed of the cart. We can get this over here and we obtain that V is equal to minus Im omega, which becomes V over R. I will put it to the side. Okay, so S plus KB squared times L over RIM times V, and I will say something over R here, okay, V over R, which comes from here, plus R KB over RM V is the expression, oh, and I forgot over S, is the expression for the V as a function of that input voltage. Now, the presence of this R reminds me of something, as well as this one, which is that there is a collision between that R, which is a radius, with the R from the resistor, which appears here and here. So for that purpose, I am going to call this guy not R, but L. L like a length. What this leads us to changing is, first of all, this term, which becomes L. Oh, and then we have the inductance of the motor. Okay, there goes another problem. So we cannot call it L. We will try small l. Okay. Under these conditions, we now have a palatable expression, which we can simplify by putting all the v terms to the left. And we obtain 1 plus Im over L times Kb squared L divided by Rim. So we have the same term here and there, which we will now erase. Plus Im over L times S must be equal, unless I am badly mistaken, to R Kb over Rm times V over S. And we have the small v appearing here. Or, finally, we obtain that V is equal to the following terms. I can erase this. And I get that V over the input voltage is equal to R Kb divided by Rm times 1 over S times 1 over 1 plus Kb squared L over R over Lr plus Im over L times S. I do not guarantee the exactness of this expression, but I want to show its general expression, or the idea of its general expression, which is that V over small v, over big V, sorry, is equal to a certain coefficient K divided by S times a certain coefficient 1, in this case, over 1 plus, or sorry, let me simplify this even more, over K prime plus A times S. It is the product of two first-order transfer functions, which are well understood. We then can write the expression for not only the speed, but the output voltage, which I think we call Vs, S for sensor. And that will be equal to a certain coefficient times V. I forgot what its expression was, but what I read is that Vs is equal to K times omega S, okay, the speed of the sensor, and with V equal to, we called it R, but that doesn't work, so we're going to call it K prime times omega S. We end up getting that Vs, the voltage across the armature of the sensor, is equal to K over K prime times V, the speed of the motor. And of course, we have V here as a function of the input voltage. So this Vs, which is the output voltage, which we can also capitalize in order to make it look like the input voltage, is a second order transfer function of the input voltage. We could further simplify this transfer function, but I would rather keep it as it is. And write that the general expression will be for V, the output voltage, equal to the output voltage Vs over V will be a constant A over S times 1 over, let's change notation and call it B plus Cs. That's the general expression. And what it says is that the response of an input voltage which is held constant by the output will be a ramp filtered by a first order transfer function. Now that we have derived the transfer function from input voltage to output voltage, and we have a clear relationship between the output voltage and which is measured and the speed of our cart, we can move to the logic that we will try in order to change this, to affect the characteristics of the car. Again, this is not a design course, but just a way for you to understand the relationship and the value there is to mix mechanical elements with electronic elements. So let's recall that the transfer function from output voltage to input voltage is A over S times 1 over B plus CS, and that we have Vs equal to K over K prime times V. And let's erase the rest of this transparency. So here we go. We are done. And we are left to a simple expression. We should simplify it even more by writing that Vs is equal to some coefficient, which we will call alpha times V, where alpha is equal to K over K prime. These exaggerated simplifications are extremely useful so we can keep track of the essential elements of what we're doing. So our system ends up looking like this. If I draw it, we're going to have a desired voltage, and I'm going to switch colors. V desired, oh sorry, it's not a desired voltage, my mistake. It is a desired speed, which I call V desired. I have my actual speed V, and V as a in cursives, okay, like this. And as I said, we're gonna take and compare these two voltages for the purpose of designing a box here, okay, such that we feed all these into the motor and the cart, so that its speed V, which is also the corresponding voltage Vs, okay, K over K prime, and it gives us Vs, can be used, assuming a proper transformation from Vs back to V, which would be K over K prime over K, to invert this operation, can lead us to the system following the desired speed. So the area I circle in red is the mechanical system. And it is often called the plant. The transfer function from input voltage to output voltage is this guy. That part is the controller. And there remains for us to build this controller. I temporarily erase the plant for the purpose of focusing on the controller. So there are a few elements that we need. We need to do k prime over k. We need to compare v desired and v. And finally, we need to build k. So all these can be built via electronic components. K prime over k, for example, provided that it is positive, which it always is, can be built by mounting in series 2 op-amps, 1 op-amp with a resistor here, a resistor in the feedback loop, and an output with the other elements being traditionally linked to the ground. And so we have a minus here and a plus here. Okay. And then if the input is Vs, if we choose R and R prime to be equal to K prime over K, then the output will be minus K prime over K times Vs. We can now pass this through an other op-amp design. I'm not saying that this is the most economical design, but it is certainly doable. With the same minus and plus here, the same link to the ground here, two identical resistors here. And then what we get at the output is K prime over K times Vs. So this element here allows us to build this guy there. Now noticing that eventually we take a minus sign here. Okay, so we invert the sign, and we have already inverted the sign here. Two minuses give a plus. And so we can erase this part in order for our design to encompass not only what I've shown here, but also the minus sign there. Okay? Now, all that remains is to add this signal with that signal. Now, we have seen how to do that by doing the following. I'm going to erase my drawings here to concentrate on the next drawing. And again, since our designs account for the minus sign here, okay, what we're going to do is we're going to try and take into account both this guy and the number k here. So for that purpose, I build this adder that we have seen before, and the adder is made of two inputs, which corresponds to the two voltages V, what we be more precise, minus V, and V desired. So we have, let's say, V desired here and minus V there. We put two resistors here. We link them together to an op amp plus, sorry, my mistake, minus and plus. I connect the other end to the ground, and what I will do here is I will make an adjustable resistance. Okay, so I will use a dial here whose resistance value can be changed. This is fairly easy to do and will give us lots of interesting stuff. The output of this guy, given these two guys, I will call VE. This variable resistance, we can call it R sub V for the purpose of saying that it is variable. Now, if we do that, then we know that VE is going to be equal to RV over R times V desired minus V. And again, V desired is in cursive, my mistake. V desired. Let me clear that out. And rewrite this as V desired. So the output voltage is equal to RV over R times V desired minus V. Okay. Now this V is a speed. That V is a speed, but through the transformation over K prime over K, what we should say is that this is a voltage, that is a voltage which correspond to the desired speed and the actual speed. So these are actually voltages, but their values are the same as what we wanted. So by varying RV, we can vary K, which is RV over R. Now there is only one difficulty, which we have a minus before, but we can always use an inverter circuit that we have already seen in order to get the proper signal here. So as we do this, we have now completed our system. We have this forward loop, we have this feedback loop, and it is now time to see what effect the system, this logic, has on that system. So In order to simplify things, I will say the following. On the one hand, we have Vs over V, the input voltage, equal to A over S plus times 1 over B plus Cs, where A and B are complicated functions of constant parameters. Now, we have the following system. In simplified forms, we have V desired here. We have a number K here. We have the system, the plant, okay, which we're going to write as A over S plus, my mistake again. So A over S times 1 over B plus Cs. We obtain at the output Vs, and we also have as an output through our little sensor K prime over K. Okay, we actually also have a measure of V. Okay, then we have the feedback loop followed by a minus here and a plus there. All this is electronics, that is mechanics. I will assume for simplicity that this is equal to 1, that A, B, and C are also equal to 1. That way, we obtain a much simpler system for the purpose of simplifying our analysis. We have VD here. We have the difference here. And again, we'll talk more at length about how all this works. We have the parameter K here, which is tunable via our variable resistor. And we have a system, a model, that looks like 1 over S times S plus 1. We have V at the output, and we feed V back into the system. Now, again, we have a bunch of electronics hidden, but we've seen that we can do it. We're going to keep it that way. I remove this guy, and I ask what values, or what is it that I can obtain in terms of response for that system. We first need to compute what is called the closed loop transfer function. Okay, so closed loop system. We call it closed loop because we have this guy and that fits back into this guy. For that purpose, we call this guy E, and we have that E is equal to VD minus V. On the other hand, we have V is equal to K over S times S plus 1. By taking this V and filling it into here, oh, my mistake. We have V is equal to K over S times S plus 1 times E. So now we can replace V by its value here, and we obtain that V is equal to K over S times S plus 1 times VD minus V, or V times 1 plus K over S times S plus 1 must be equal to K over S times S plus 1 times VD, or in other terms V. My mistake. Let me redo this. No, we have the proper expression. Okay, so we obtain that V is equal to K over S times S plus 1 divided by 1 plus K divided by S times S plus 1 times VD. We can simplify this transfer function by writing it and by reducing everything to the same denominator. And we get an alternative expression, which is V is equal to K divided by K plus S times S plus 1. So this is our final expression for V as a function of VD. Now, we can use first the limit or the initial or final value theorems to see that V at infinity, if we go back to the time domain, will be equal to VD. So the system actually reaches the speed that it is supposed to reach. In order to understand the rest of this expression, I need to call Scilab. So we're going to use Scilab, and we're going to use it for the purpose of trying different values of K. So we're going to write a small Scilab program, and we are hopefully going to be able and program a little program that will allow us to solve this problem. We will first remove the help browser for now and just open a small script. For the purpose of convenience, I will move, oops, that didn't work. I will move the expression for V as a function of VD, okay, that transfer function, to the right. Now, to write this program, we first need to clear all variables, which you use by writing the command clear. We then are going to choose a range of values of k. And for the sake of simplicity, we're going to choose k to range between 0 by intervals of 0.2 up until the value 2. We will then define our transfer function. We'll write that the numerator is equal to 1. We're going to introduce the variable s as a symbolic variables in such a way that we are now going to run a loop for I, or we could actually erase this and just run the loop with k. Okay, so we could say for I or for k equals 0 by intervals of 0.1 or 0.2 up to 2. We're going to have to change our numerator, and we say num is equal to k. The denominator is equal to k plus s squared plus s. And we are now interested in plotting the response of the system. So for that purpose, I will look at this, and because I have an old template, okay, that old template uses the function that I'm not totally comfortable with. And hold on a second, this is not the right one. Okay, so let's see. This is not the right one. My God. Okay, for some reason I thought I had a plot function here, but it does not appear to be so. So what we're going to do instead is go back to our function, go to the help file. Let me remove useless information, and go to help and ask help sysim. Now this function is the one that we have already seen and allows us to simulate, for example, the step response of the system. Okay, so I'm going to write the following. Y, or we should call it literally V, is equal to sysim of impulse. Oh no, we're gonna compute the step. Okay, step comma. Oh, I know where this thing is. We have seen it earlier. How does it work? So let's go back to this thing, and we're going to go to my course file. We're going to go to AE3515, spring 2014, and nothing. This is very frustrating. Okay, so we're going to write the step of our system. So the syntax for the step is here. System of step over a certain time t. We have to specify t. T is equal to 0.05, and we're going to simulate over 10 seconds. So if we go back here, we get that step t and w is nothing really. Now I'm just I am just like slightly confused, and I am confused by 1 over s here. What is it? So I am okay, so we have what I want here. Step, comma, t, comma, num over den, and that is it. We then ask to plot in 2 dimensions t, comma, v. That is the output speed as a function of t. Now let's pray it's going to work. When I call this motor speed, normally if this system works, we should obtain as a response v, which eventually reaches 1. So I would like to execute this file, and I forgot how to do that. Okay, so let's go to the main directory, the console. We should be able to find a place where to find the file to execute, and it gives us a issue. So let's look at what num looks like. Den is like num over den num over, then something is wrong. The numerator is 0. Okay, so that's not correct. So we're going to crank up the gain a little bit. 0.1. Okay? Now, then what it says is we have an error, and it doesn't like the fact that our argument number 1 is not correct. Okay, so let's try and rerun this thing. Okay, now we have a proper response. And we have asked for the plot 2D thing. And here's what you obtain. In this figure, we have plotted the response of the system for growing values of k. This value corresponds to k equals 0.1, and then you have increasing values of k here. And what you see is you have a set of desired responses, or a set of desired responses, given that the desired response is here at 1. And what you see is that the different responses have different characteristics. This one is sluggish, but it does not oscillate. This one is sluggish, less so, and it does not oscillate. This one is even less sluggish, but it overshoots a little bit. And then at the other extreme value, this curve, this response, oscillates. And by oscillating, nevertheless reaches a final value which is the same as all the others. And so, by doing so, I have been able to propose to you an initial control system design paradigm whereby the mechanical system is hooked to the proper components to obtain a compound system whose response I can tune by tuning the parameter k, which is present here and in my code. As a result, I now have a design tool which is extremely powerful. We will see that many more modifications can be brought to the initial mechanical system by means of electronic components for the purpose to obtain even more different responses. Finally, we will learn how to shape the responses to our liking. Before that, next, we will look at the state space representation of all these systems for the purpose of giving you an alternative to the transfer function representation of systems. Thank you.